So welcome back. This is the part two of our writing in OS and Rust. So last day we just completed the freestanding Rust binary. So we'll be continuing to the next chapter, which is writing a minimum Rust kernel. It's I guess two streaks for the day. Let's get started. You can also read along in the blog, or you can just read along with the video. Let's go. In this post, we will create a minimal 64-bit Rust kernel for the x86 architecture. We will build upon freestanding Rust binary from the previous post to create a bootable disk image that prints something to the screen. Okay, so this table of contents, we'll have boot process, we have a minimal kernel, and then we have running a kernel. The boot process. When you turn on a computer, it begins executing firmware code that is stored in motherboard ROM. This code performs a power on self-test and it detects available RAM and pre-initializes the CPU and hardware. Afterwards, it looks for a bootable disk and starts booting the operating system kernel. On x86, there are two firmware standards. The basic input-output system, BIOS, and the newer Unified Extensible Firmware Interface, UEFI. The BIOS standard is old and outdated, but simple and well supported on x86 machines since 1980s. UEFI, in contrast, is more modern and has much more features, but is more complex to set up, at least in Phil's opinion. Currently, we only provide BIOS support, but support for UEFI is planned to. Okay, if anyone can help me. So BIOS boot. Almost all x86 systems have support for BIOS booting, including newer UEFI-based machines that use an emulated BIOS. This is great because you can use the same boot logic across all the machines from the last century. But this wide compatibility is at the same time the biggest disadvantage of BIOS booting because it means that the CPU is put into a 16-bit compatibility mode called real mode before booting so that the archaic bootloaders from the 1980s would still work. Oh, so UEFI is kind of hectic. He's right. You have to create a virtualized bootloader for BIOS, an emulated BIOS, and you also have to support UEFI based machines. That's kind of hectic. But let's start from the beginning. When you turn on a computer, it's the core stuff, you learn something from it. When you turn on a computer, it loads the BIOS from some special flash memory located on the motherboard. The BIOS runs self-test and initialization routines of the hardware. So BIOS does all the testing and initialization of the hardware. And then it looks for the bootable disk. If it finds one, control is transferred to its bootloader, which is a 512-bit, sorry, 512 byte portion of executable code stored at the disk's beginning. Most bootloaders are larger than 512 bytes, so bootloaders are commonly split into a small first stage, which fits the 512 bytes, and a second stage, which is subsequently loaded by the first stage. Okay, so the disk is divided into two parts, which the first part has the bootloader, which is 512 bytes. The second stage is the stage that is loaded by the first stage, which is the rest of the disk. The bootloader has to determine the location of the kernel image on the disk and load it into the memory. It also needs to switch the CPU from the 16-bit real mode first to the 32-bit protected mode and then to the 64-bit long mode, where 64-bit registers and complete main memory are available. Its third job is to query certain information such as a memory map from the BIOS and pass it to the OS kernel. This is what a bootloader does. First, its job is to determine the location of kernel image on the disk and load it into the memory. The second job is to switch the CPU from 16-bit to 32-bit and to the 64-bit where all the registers are available. And its third job is to query the information from memory map and from the BIOS and pass it to the OS kernel. We'll be writing a bootloader. I don't know. Writing a bootloader is a bit cumbersome as it requires assembly language and a lot of non-insightful steps like writing this magic value to this processor register. Therefore, we don't cover bootloader creation in this course and instead provide a tool named bootimage that automatically prepares a bootloader to your kernel. Okay, so we are handling all the hard stuff to the boot image, which is I don't know what is boot image though. It's boot image. Creates a bootable disk image from a Rust OS kernel. It will help us create a bootable disk. That's a bootloader, partially, you can say. Okay, so this is planned. I don't know if it's done or not. The multi-boot standard. To avoid that, every operating system implements its own bootloader, which is only compatible with a single OS. The Free Software Foundation created an open bootloader standard called Multi-Boot in 1995. The standard defines interface between the bootloader and the operating system, so that any multi-boot compliant bootloader can load any multi-boot compliant operating system. The reference implementation is in the GNU Grub, which is the most popular bootloader for the Linux system. To make a kernel multi-boot compliant, one just needs to insert a so-called multi-boot header at the beginning of the kernel file. Okay, this makes it very easy to boot an OS from the Grub. However, Grub and multi-boot standard have some problems too. They support only the 32-bit protected mode. This means that you will still have to do the CPU configuration to switch to the 64-bit long mode. They are designed to make the bootloader simple instead of the kernel. For example, the kernel needs to be linked with an adjustable default page size because Grub can't find the multi-boot header otherwise. Another example is that boot information which is passed to the kernel contains a lot of architecture dependent structures instead of providing clean abstractions. Both Grub and multi-boot standards are only parsed documentally. Oh, so it's hard to read then, I guess. Grub needs to be installed on the host system to create a bootable disk image from the kernel file. This makes development on Windows or Mac more difficult. We should skip this. It's kind of like it's going the different way. May need to make your own kernel multi-boot compliant, but we don't need to do this as you're building a bare metal. So because of these drawbacks, we decide to not use Grub or multi-boot standard. However, we plan to add multi-boot support to our boot image tool so that it is possible to load our kernel on a Grub system too. If you are interested in writing a multi-boot compliant kernel, check out the first edition of the block series. Oh, so they did write a multi-boot compliant kernel, but as multi-boot compliant kernels require multi-boot compliant bootloaders, that would be tough for us. What's our take? Should we build it? But it would be the first edition. First edition is not supported. It would be a roadblock for us, I guess. We'll look at after we complete this series. We'll complete all those, creating our own bootloader, creating a multi-boot compliant bootloader. We'll do that after this series ends. So UEFI. We do not provide UEFI support at the moment, but we would love to if you would. Okay. So we are skipping UEFI and using just the BIOS. Now that we roughly know how a computer boots, it's time to create our own minimal kernel. Our goal is to create a disk image that prints a hello world to the screen when booted. We do this by extending the previous post pre-standing Rust binary. As you may remember, we build the pre-standing Rust binary through cargo, but depending on the operating system, we need different entry points and compile flags. That's because cargo builds for the host system by default. That is the system you are running on. This isn't something you want up for our kernel because a kernel that runs on top of Windows does not make so much sense. Instead, we want to compile for a clearly defined target system. Installing Rust nightly. Rust nightly is a version of Rust. It is different from Rust cause it supports many other options like which are not much stable on Rust, and it is widely stable on Rust nightly. And it's not an official version. Like if stable is widely used by everyone. Beta is like standard, which is passed through nightly to the beta, and then beta passes to stable. That's how shit works, I guess. The Rust book explains the difference between these channels really well. Sorry. So take a minute and check it out. We're building up. Okay. Okay, I just explained to you, and I don't even know. It's right. Let's just take a look. I get it. That's nightly beta drops something here. It executes something which is like it's transferred to beta, and then something stable is yeah. I was right. For building an operating system, we will need some experimental features that are only available on the nightly channel. So we need to install a few nightly versions of the Rust. To manage Rust installation, we highly recommend RustHub. It allows you to install nightly data. Okay, I have RustHub, I guess. What we need to do now? That's nightly for the running stuff. Alternatively, you can add a file named Rust toolchain with the content nightly to the project's tool directory. And check that you have a nightly version installed by Rust C version. Okay, let's do this. Alright, we have why did that happen though? It's happening. Oh, sorry. That's my mistake. We have 1.89.0. And what version do we need? It doesn't contain dash nightly at the end, the nightly in palace. So let's just rust C, rust up, override, set nightly. Now, if you do this rust version, you should get nightly. We are getting nightly. Nightly compilers allows us to opt into various experimental features by using so-called feature flags at top of a file. For example, we could enable experimental ASM macro for inline assembly by adding feature ASM to the top of our main RS. Note that such experimental features are completely unstable, which means that future Rust version might change or remove them without prior warning. For this reason, okay, it is absolutely necessary. So nightly is completely required for this blog target specification. Cargo supports different target systems throughout the target perimeter. The target is described by a so-called target triple, which describes the CPU architecture, the vendor, the operating system, and the ABI. For example, the x86-64 unknown Linux GNU target triple describes a system with an x86-64 CPU, no clear vendor, okay, and a Linux operating system with the GNU ABI. Rust supports many different target triples, including ARM, Linux, Android, ABI for Android, and WASM32 unknown for WebAssembly. For our target system, however, we require some special configuration parameters to underlying operating system. So none of our existing target triple fits. Fortunately, Rust allows us to define our own target through a JSON file. For example, a JSON file that describes the x86-64 unknown Linux GNU target looks like this. You need to create a target, right? It has a LLVM target, which is like the operating system, the GNU, which is ABI, and the data layout. I don't know what is that. It supports 64, I28. I guess it's the integers they support. It is arc. its architecture is actually it's target Indian little. I don't know what's all OS is Linux executables link of flavor GCC. It's C related to C I guess. Most app calls. I don't know what it is. Though. Most fields are required by LLVM to generate code for that platform. For example, the data layout field defines the size of various integers, floating point, and pointer types. Then there are fields that Rust uses for conditional compilation. Wait, are we recording? Yeah, recording. Yeah, where were we? Then there are fields that Rust uses for conditional compilation, such as target pointer with. The third kind of field defines how the grid should be built. The third kind of field, which is that. For example, the pre-link arguments field specifies arguments passed to the linker. Okay. We also target x86-54 systems with the kernel, so our target specification will look very similar to the one above. Let's start by creating our own. Oh, let's create this. Just creating. That is x86, 64, unknown, and none. Sorry. Oops. I was copying the LLVM name, not the name provided. Blog was touches on. And we need to do what? We need to fill this. So it will be this JSON file which has a LLVM target. And it is, yeah, that's right. The spelling is wrong. And we have a data layout. It's so good device. It is so good layout. It's the layout. I can copy this, right? So I can copy this. It's not our terminal now. We have everything up here. Shift it. So we can get all this. Note that we changed the OS in the LLVM target and OS field to none. Okay, change it, yes. And we remove these pre-link arguments or as well, I guess. Yes, we did. Because we will run on bare metal, we add the following build related entries, link of flavor, LLVD. Let's add these. Link of flavor, link of flavor, LLD, and we will have linker Rust LLD. Yes, so cool of GitHub Copilot. Instead of using the platform's default linker, which might not support Linux targets, use the cross-platform LLD linkers that is shipped with Rust for linking our kernel. Setting specifies that the target doesn't support. Yeah, so we are adding that over here as well. We did it in the normal file as well. Panic strategy, and it's going to be abort. The setting, yeah, we know this. Not in contrast to the cargo terminal option, this target option also applies when we recompile the code library later in the post. So even if you prefer to keep the cargo terminal option, make sure to include this option. This is for, oh, this literally God's work. We are writing a kernel, so we will need to handle interrupts at some point. To do that, just remove the GitHub Copilot. It's helping, but it's not so much needed here. Because you're learning, right? You need to learn. We are disabled red zone because of the build issues. We're writing a kernel, so we need to handle interrupts at some point. To do that safely, we have to disable a certain stack pointer optimization called red zone because it would cause stack corruption otherwise. For more information, see our second post about disabling red zone. So a red zone is a stack pointer optimization, and we need to disable it. No, we need to enable it. If you disable red zone, would disable red zone, right? Yeah. The features fields enables disables target features. We disable the max. We will disable the MMX and SSE features by prefixing them the minus and enable the soft load feature by prefixing it with a plus. Note that there are no spaces. Okay, what is the features by the way? It is MMX and it is SSE. Oh, this comment and there is soft load. Soft load. So well, and that's all. Our target is built. The feature, yeah, this the mimics and SSC features determine support for single instruction, multiple data instructions. I don't know what's that, which can often speed up programs significantly. It's for speeding up the program, the mimics and SSC features. However, we are using the large SIMD registers in OS kernels leads to performance problems. The reason is that the kernel needs to store all registers to their original state before continuing an interrupted program. This means that the kernel has to save the complete SIMD state to main memory on each system call or hardware interrupt. What does that mean? That's a hectic task, I guess. Since SIMD state is very large, that is 1600 bytes, an interrupt can occur very often. These additional save restore operation considerably harm performance. So for smaller systems, this will harm performance. That is what I'm getting from this. To avoid this, we disable SIMDB for a kernel, not for our applications running on top. So kernel doesn't uses this to store the origin state because it is quite larger than our bootloader kernel. Kernel is like 512 bytes, I guess, and storing the SIMD state, which is much larger than that, would obviously cause performance issues. A problem with disabling SIMD is that floating point operations on x86-64 requires SIMDB registers by default. Okay, so x86 requires SIMDB registers by default. To solve this problem, we add the soft load feature, which emulates all floating point operations through software functions based on normal integers. So we'll use the soft load feature, which emulates all the floating point operations through software functions based on the normal integers. So it's an emulator for soft load for the floating point integers, and I don't know why do we need to specify it correctly with which we will be using this in future. I don't know about that. Here disabling SIMD post, SIMD post. As you want to use what is Rust C ABIX 86 soft load. I don't know. Should we add this? As I'm doing the SoFlow feature, we also need to not test the Rust compiler Rust C that we want to use the corresponding ABI. We can do that by setting the Rust C ABI field to x86. Okay, do this. Rust C ABI. I don't have that. I don't. I checked it. It's giving me some kind of error. SoFlow. Now putting it together, our target specification file now looks like this. Looks like yes, it looks like this. Our architecture. Our target endian is little. Our target point of width is 64. Our target saint width is 32 and OS is. Our link of flavor is LD, and our linker is Rust LLD, which ships together. Our panic strategy is abort, and our disable red zone is true. Our features are this, and our features are right, yes. And our Rust ABI is 86 software. Building our kernel. Let's build our kernel. Uh, so we need to compile our new target. Compiling our new target will use Linux conventions. Since the LD linker flavor instructs LLVM to compile with the flavor GNU flag. For more linker operations, see the Rust C documentation. This means that we need an entry point name start as described in the previous post. We have that. Here we have that. This is the 15 lines of code we did yesterday, and we'll use it. Note that the entry point needs to be called start regardless of what host OS. Now we can build the kernel for our new target by passing the name of the JSON file as the target. So we'll specifically build for the target cargo build target. Let's name x86 64 blog OS. Doing quiz speed. What kind of error do we got? Failed to run Rust C. There are different errors in mine to kind of fix those. What are the errors they got? So they did got the error as well. Stuff such as option and is implicitly linked to all no SCD fields. The problem is that the core library is to build distributed together with the Rust compiler as a pre-compiled library. So it is only valid for the supported host triples, for example, this, but not for a custom target. If you want to compile code for the targets, you need to recompile code for these targets first. That's why it didn't work because this target specification is not in the library as we're not using any library and it is pre-compiled with those. So let's just recompile our target. So we need to do those first. That's where the best build std feature of the cargo comes in. It allows to recompile core and other standard library creates on demand. Instead of using the pre-compiled version shipped with the Rust installation, this feature is very new and still not finished. So it is marked as unstable and only available on the nightly Rust compiler. So this is super great. We don't need to install the pre-compiled versions. We can compile them on our own on our demand using the build std feature. This is, I guess, nightly wins over here. To use the feature, we need to create a local cargo configuration file at .cargo config.toml. The cargo folder should be next to our src folder with the following command. Where do I add those? I need to create a new cargo folder. This is kind of clear. To create a .cargo folder and which will have our. Let me just. Ah, and it up it. That's good. It's putting OCD on it. It's very long. So it's created in cargo. We have to get cargo.tom config.tom and we have to add the stable version stable recipe and we need to build core. We need compiler of core. We need compiler. We need compiler built-ins. That's all we need. This tells cargo that It should recompile the core and the compiler built-in library. The latter is required because it is dependency of a core. In order to recompile these library, Cargo needs access to the Rust source code, which we can install with the Rust top component add Rust SRC. So let's add it. We need to add the Rust up, and this is what is line Rust up component and add Rust SRC. This should do the info component is up to date. I have this. Note: the unstable build std configuration key requires at least the Rust nightly from da. Yeah, the latest one. After setting the unstable build configuration key and installing the rest as RC component, we can return our build command. Let's do this. Still got me error. Still got me error. Is compiled, but mine is failed to run rest C to learn about target sourcing caused by process didn't exit successfully. Why did it happen though? Said invalid type. There's some errors here. To see them properly. The process didn't exit. I'm honestly stuck over there. I don't know how to do it. Is this something I it should run this Rust? SCC Rust works. SC works. It just doesn't try it. It does. Rusty does work. That doesn't mean you just fuck up some code over here. When dot cargo, which is just alongside the SSC file, you just clear it right. We added the core, added the compiler built-ins. What's wrong then? Just check if someone has put the same errors in the comments. There's some problem with our target, I guess. You just copy their target, what they did on the target, and just see it as the error. It's and the summary. There's problem with our target file, which I can conclude from this. No, it happened again. Don't know why it's happening. Expected a string at line 6 column is expecting a string. It's weird. Expecting a string, so let's add the string. See if it works now. It is compiling. It is yeah. So this error it's string now. It's not integer, but it is like I have it somewhere controller. somewhere up there. Specified was. Yeah. So then there is such as target pointer with the three kind of field defense how crate should be built. For example, the feeling governance. I don't know what's up. There's some. So you can change this to string, and now it does go right. Where were we? Where were we? Where were we? We were on. We just built our kernel. We just did the build std option, and now we were on the memory related instance. So now, as our build is successful, now we're just moving to memory related instances. Intrinsics. I don't know what's that. The Rust compiler assumes that a certain set of built-in function is available for all the systems. Most of these functions are provided by the compiler built-in crate that we just recompiled. However, there are some memory functions in that crate that are enabled by default because these are normally provided by the C library on the system. These functions includes memset, which sets all bytes in a memory block to a given value, memcpy, I guess copy, which copies one memory block to another, and memcmp, which compares two memory blocks. While we don't need any of these functions to compile our kernel right now, they will be required as we add some more code to it, like copying stuff around. Since we can't link to the C library of the operating system, we need an alternative way to provide these functions to the compiler. One possible approach for this could be implementing our own memset extra, memset, memcopy, and memcompare functions, and apply the no unsafe no mangle attribute to them. To avoid the automatic renaming during compilation, however, this is dangerous since the slightest mistake in the implementation of these functions could lead to undefined behavior. Yeah, so it's not supported, and we need to create our own functions to move stuff around. For example, implementing memcopy with a for loop may result in an infinite recursion because for loops implicitly calls info iterator, info into iterate. I guess I've used this one. Uh, Create method which may call memcopy again. So it's a good idea to reuse existing well-tested implementation instead. And it saves time areas too. Fortunately, the compiler building crate already contains implementation for all the needed functions. These are just disabled by default to not collide with implementation from the C library. Oh, so compiler built-ins have these functions, but as C library have those, so we just disable those. But as we need it now, we can enable this. This is like best case scenario. We can enable them by setting cargoes, build SCD feature flag to compiler build ins map. I'll just change it. We need to add this in terminal. Here, let's add it. Need to add a build steady feature equals to compiler built-ins dot. No, it's not that. But we have compiler built-ins, man, and this has all the functions we need. Does it have just mem, or we have all the copy and compare functions as well? We can enable them. Yep, I did it. Like the build a cd flag. The flag can be either passed in the command line as a uh, Z flag or configured in the unstable table in the carbon. Since you always want to build with this flag, yeah, this makes more sense. Support for my feature was only added very recently, so I need to at least rest nightly. Yeah, I know that. Behind the scenes, this flag enables the main features of the compiler between players. The effect of this is that the unsafe no mangle attribute is applied to the mem copy after implementation of the code, which makes it available to the linker. We need to create those. And with this change, our kernel has valid implementation for all compiler required functions. So it will continue to compile even if our code gets more complex, etc. Define a target. Sorry. So with this change, uh, yeah, to avoid passing the target parameters on every invocation of cargo build, we can override the default target to do this. We add the following to a cargo configuration file. So we'll add these are the unstable files for build. Like we can have target as simplification of that. It was very hectic, but I had CMD features. No. I'm so bad at typing while recording. This tells cargo to use our target. Yeah, I know this. Now able to build for a bare metal with simple cargo. I will start entry point, which will be called by the builder. Is still empty, and it's time to type it. Yeah. So now here the deal comes. Depending something to the screen. The easiest way to print text to the screen at this stage is the VGA text buffer. It is a special memory area mapped to the VGA hardware that contains the content displayed on the screen. It normally consists of 25 lines, 25 lines that each contains 80 character cells. Each character cell displays an ASCII character with some foreground and background colors. The screen output looks like this. This looks like gibberish. We'll discuss the exact layout of the VGA buffer. What's this? So it's ASCII codes. What's this about? It's, these are all ASCII codes. I didn't know this. We'll discuss the exact layout of the VGA buffer in the next post, where we write a first small driver for it. For writing hello world, we just need to know that buffer is located at an address 0xb8000 and that each character cell consists of an ASCII byte and a color byte. So each character cell consists of an ASCII byte and a color byte, and our buffer is stored at 0xb8000. So if we write something to this address and then it will be shown on our screen. That's how it works. Implementation looks like this. We have a static hello, which has a U8 address, and we are adding hello world to it. Now, pub extend, this is a start function, so it lets VJ buffer to this address as a pointer. And then this is a for loop in this hello dot iter dot enumerate, which writes each word, I guess. Now we have unsafe attribute. I don't know what it is. It writes VGA buffer dot offset I as I size. So it's for the sky code, sky byte. So it's a sky byte, and the other one is the color byte, which is 0xb. What is 0xb? So yeah, it's storing to the integer, and as the integer is 2 bytes, and the color is just a single byte. Just that's why I'm adding the plus one over here, and it's the loop. So yeah, let's just add it in our main.rs to have the static hello, and then we have to add this u8 hello world. And then in the start function, we need it doesn't return, right? It doesn't return. So a VG buffer, it is 0xb8000 as a integer, as a pointer, and it is we can now modify it for now we're creating a for loop for this. We're passing the reference here. I don't know. Oh my God, I'm so bad. Enumerate and save vg buffer dot offset is I size goes to the byte, and we have another for the color of the IF star 2 plus 1 for the 1 byte. Uh, it is 0xp. It's done. Should work now according to this. First, we cast integer 0xp8 into a raw pointer. We did it over here. Then we iterate over the bytes of the static hello byte string. We use the enumerate method to additionally get a running variable I. In the body of the for loop, we use the offset method to write the string bytes, and the corresponding color byte 0xp is a light cyan. Note that there is an unsafe block around all the memory writes. The reason is that Rust compiler cannot prove the raw pointers we create are valid. They could point anywhere and lead to data corruption. But as we know, buffer is stored on those, so we are safe for now. Basically telling the compiler that we are absolutely sure that some operations are valid. Note that the unsafe block does not turn off Rust safety checks. It allows you to do five additional things. What are those five additional things? I'm curious. What are we allowed by this unsafe attribute? Unsafe superpowers. Dereference a row pointer, call an unsafe function, access or modify a mutable static variable. That's shady. We just did it. Implement an unsafe trait and access fields of a union. Yeah, it's good to know. I want to emphasize that this is not the way we want to do things in Rust. Yep, it's bad. It's very easy to mess up when working with raw pointers inside unsafe blocks. For example, we could easily write beyond the buffer cell and beyond if we are not careful. So we want to minimize the use of unsafe as much as possible. Rust gives us the ability to do this by creating safe abstractions. For example, we could create a VGA buffer type that encapsulates all unsafety and ensures that it is possible to do anything wrong from the outside. This way, we could only need minimal amount of unsafe code and can be sure that we do not violate the memory safety. We will create such a safe VGA buffer abstraction in the next post. Yeah. So we'll be creating a VGA buffer abstraction, and yeah, it's much more cleaner than writing these buffer values over here. Running our kernel. So let's create the kernel. Now that we have executable that does something perceptible, it is time to run it. First, we need to turn our compiled kernel into a bootable disk image by linking it with a bootloader. Then we can run the disk image in the QEMU virtual machine or boot it on the real hardware using a USB stick. I guess QEMU virtual machine is nice. I don't have a USB stick with me right now. Creating a boot image. To turn our compiled kernel into a bootable disk image, we need to link it with a bootloader. As we learned in the section about bootloading, the bootloader is responsible for initializing the CPU and loading our kernel. Yeah. Instead of writing our own bootloader, which is a project on its own, we use the bootloader crate. The crate implements a basic BIOS bootloader without any C dependencies, just Rust and inline assembly. To use it for our booting a kernel, we need to add a dependency on it. In Toml, we need to add a dependency. Yeah, that's not. Yeah, here it is. And a dependency, we need to add bootloader. Bootloader. This version is zero point 0.9. Note the post is only compatible with bootloader. Newer version use a different build system and will result in a build errors when following this post. Adding the bootloader as dependency is not enough to actually create a bootable disk image. The problem is that we need to link our kernel with bootloader after compilation, but Cargo has no support for post-build scripts. To solve this problem, we create a tool named boot image that first compiles the kernel and bootloader and then links them together to create a bootable disk image. Install the tool, go to your home directory and execute the following command in your terminal. Cargo and stored boot image. So boot image first compiles both the uh, kernel and the bootloader and then links them, which is not how post build scripts run in Cargo. So we need to have boot image on our system. Cargo and stored boot image. Ubuntu Cargo install boot image. Now we have boot image installed. This was fast. For running boot image and building the bootloader, you need to have LLVM tools to preview Rust up component install. You can do so by executing Rust up component add LLVM tools preview. After installing boot image and adding the LLVM tools preview component, you can create a bootable disk image by going back into your cargo provide project directory and executing cargo boot image. We are in no directory cargo. Boot image. One in cargo manifest here. Bootloader build failed. Then there is. Now they expect line 13 should also have a iodum. So it now says it's not a string. No, it is just integer. Now it's just an integer. It's kind of dumb. And I'm very bad at reading the RMA as it was like bootloader was building and now it failed. Is it somewhere straight away here? Well, to crazy. Nobody had these arrows with them. No. Should work. Should work. It should work from now here, but it is the error is still up and running. These are the errors. But there is no light in 13 now. And this is the column 3 actually. But there is this should be string as well. Oh, you're saying this? Nah. Switching that should not that's invalid time, right? It's also invalid type. I just did it. There's 64 over there. But it's expecting a string over there. I guess there is some kind of change in how the targets work. I guess this is how. So how does it work now? I don't know. It should work. Says it's running fine. It's using PGO. It's test coverage. It's not talking about our issues. It's Rusty book is different. I haven't tried the Rusty book. Does it cover about hitting on targets? I don't know why it is happening. Let's ask GPT to just tell us what's wrong with this. Tried creating a custom git log set with this. We compile for custom that is for 24-bit. I'm not using 24-bit. I'm using 64-bit. If you have a forum over there. Let's see if it's- I'm only working on the tribute kernel. For this, I use target. How I do it is no target pointer must be shown. Well, must be in it. I don't know the so how they are linking the opportunity test it out. Change the make target pointer with in target JSON as integer. We'll do that for the target kernel with the integer. We'll do that for target pointer with as well. It's not working though. If I just build cargo boot image, I get it. So this supports not doing this, and this supports doing this. So it's causing us the error. It's causing this error. How do I fix it? I think this is super old. This is super old. We have an R in the recording. But here, I just ask this AI guy we have with this. Let's see if we can handle it. So let's try and do this. It's an agent. And so the Rust pool has now implemented this as well as an integer. But if I do it as an integer, it's causing issue. Yeah, it suggests me this is, but it is not happening right. If I do this, uh, I have already done this. Is it is it some kind of it's not even looking at my code. I've already done it. Still the error persists. Maybe it's going to this. I would think. I have all the characters from it is building, it's failing right. So it's called clean everything and we need to add everything again. Rust up. It's rust up or rust C. It's rust up, I guess. Rust up override set 90. Rust up override set 90. That's what I did this. Now I'm did it. Rust component add rust SRC. Just copy these. Sorry. I don't know what I did. Fuck. What the fuck? What did I just fix? Yeah, it should happen. Just you need to do cargo. You need to add these tools. I just add to the control C over here. Now I just write cargo mm, boat image. It should run the build fields again. Yeah, I fixed. Yeah, there was nothing but the newer build doesn't require it to be string. It was all right. The blog specified the right GS on for our target. There was no need to put it as a string. It is successfully built now. And change nothing in the code. So let's move on to the next one. We see that the tool recompiles a kernel using the cargo build, so it will automatically pick up any changes you make, or afterwards it compiles the bootloader. It took a while, it took 19 seconds. Uh, like all K dependencies, it is only built once and then cached. So subsequent builds will be much faster. Finally, boot image combines the bootloader and your kernel into a bootable disk image. After executing the command, you should see a bootable disk image named boot image blog was been in the target x86 blog OS debug. Target x86. Yep, here it is. We have debug directory, which has the boot image blog OS. Just check here. It is the one, right? Blog OS. I have boot image blog OS. Yep, here it is. You can boot it in a virtual machine, copy it to a USB drive to boot it on a real hardware. Note that this is not a CD image, which has a different format. So burning it to a CD doesn't work. How does it work? The boot image tool performs the following step behind the scenes. It compiles a kernel to an ELF file, compiles the bootloader dependency as a standalone executable. It links the bytes of the kernel ELF file to the bootloader. So that's what the boot image tool does. So boot image tool is kind of exquisite on 0.9, I guess. It doesn't allow executable binaries on other versions. That's how I came across in these files. So now booting it in QEMU. Uh, now, when booted, the bootloader reads and passes the appended ELF file. It then maps the program segments to virtual addresses in the page table, zeros the .bss section, and the sets up a stack. Finally, it reads the entry point address of a start function and jumps to it. So when booted, the bootloader reads and passes the ELF file. It then maps the ELF file to the virtual to the bootloader. It zeros the .bss section and sets up a stack. Finally, it reads the entry point address of a start function and jumps to it. Okay. Booting it in QEMU. You can now boot the disk image in a virtual machine. To boot it in QEMU, execute the following command. Okay, let's copy it. Oops, 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 oops. Oopsie doopsie. I just forgot to press that was just Control C. Can I just paste it over here? Simply like this. Fix failed to create. I don't know what this is. We have successfully did. We have oh, nice. They just not write it correctly. They just not write it correctly. I didn't write panic. Oh, just like the hello world nice. Yep, we have did something. We have did something. It is hello world. We have hello world on our screen. It's nice. And now what we need to do, we see that hello world is visible on the screen, real machine. It is also possible to write it to a USB stick and boot it on our real machine, but be careful to choose the correct device name because everything on that device is old. Yeah, so nice. We have done the task for today. It took us quite a time because of that silly error from the Rust versions mismatch. Now the real machine, it is yeah, you can do this using cargo. And to make it easier to run a kernel VM, you can set the runner configuration key for the cargo. In the config terminal, we can add is config terminal. There it is. The config terminal, we can add the new. How do you do this? We have target, target dot cft, target os, which none, and then we have runner, which to boot image runner. Now we can use the cargo run function, I guess. The target dot series as table applies to all targets where target configuration OS field is set to none. This includes our x86 64 block OS JSON target. The runner key specifies the command that should be invoked for cargo run. The command is run after a successful build with the executable path passed as the first argument. See the target of the thing. So we need to build it first, then after doing this. Nice. Specially designed to use to be unstable as a runner executable. It links the given executable with the project bootloader dependencies and then launches QEMU. What is QEMU though? I don't know about much that though. Just know that it gives me a screen to put. It's a virtual computer or something like that. For more details and possible configuration. Now we can use the cargo run to compile our kernel and boot it in the menu. Yeah, we can do that. We can do that. So that's for all for today. We'll just continue with the next blog. It was quite hectic today because of those errors, silly errors. Those were not errors, by the way. You can now reproduce this with your all, and you can even follow me along this journey. And thank you. Let's see if I can be motivated enough to go to the next blog. GG's. See you tomorrow.